Conducting market simulations. Why do we need to conduct market simulations? Because examining just utilities and importances only gets you so far. Average utilities cannot tell the whole story. So, which color is preferred in this case? Consider the following utilities. If you look at the average across 3 respondents for each color, we see that red has the highest average preference. But does any one respondent prefer red the most? No. However, if respondents choose their preferred color, we see that blue is chosen twice, while yellow is chosen once. Red isn't chosen at all. That's the opposite pattern suggested by the average utility scores. Although we originally contrived the previous example to illustrate a theoretical point, we have seen these same issues in force in actual conjoint analysis studies. Many years ago, we received a phone call from a client of ours who had conducted a CBC experiment on the subject of sport utility vehicles. She had written a market simulator in Excel and was getting shares of preference that mostly lined up with average preferences for SUV models, with the exception of one vehicle. That vehicle was near the top in terms of average utility across the sample, but was much nearer the bottom in terms of share of preference from market simulations. To investigate, we used latent class analysis to create 10 relatively homogeneous segments. For many of these segments, this particular SUV vehicle was second or third most preferred. But for no segment was this vehicle the most preferred alternative. As soon as we saw this, it reminded us of this contrived example we had been using in market simulation trainings for years. Market simulators focus on predicting choices, which, while quite related to average preferences for the sample, is not always the same thing. So, why do we conduct market simulations? Because competitive effects matter. Assume 80% of the market prefers round widgets, and 20% prefers square ones. Which should you take to market? In the absence of any other information, round would be the logical choice. But what if there are currently 10 competitors in the market, all only offering round widgets? You might decide to produce square ones. This may seem like a trivial point, but it is often overlooked in market research strategy development. Market simulators find the opportunities in the intersection of respondent preferences and the current competitive landscape. Simulations better reflect real-world behavior. For example, they represent idiosyncratic behaviors of segments and individuals. Remember, you don't have to appeal to the fat part of the market to carve out a profitable business. Market simulations also give you a choice laboratory for testing multitude of real-world possibilities. And the results are expressed in terms that make sense to management and are actionable. Go to sawtoothsoftware.com/baseball. Click Next and skip the CBC questions. Click through the 2 screens of counting tables and charts. Now you'll see the simulator. Change the prices or the wait times for the different food options. Click the Simulate button and immediately see the new predictions of share of choice. There are 3 important qualities which should be present in a good market simulator: differential impact, differential substitution, and differential enhancement. Let's look at each of these in a little more detail. The term differential impact means that the impact of a marketing action depends on the extent that the alternative is near the purchase threshold. A simulator that reflects differential impact focuses attention on customers on the cusp of buying the company's offer. Respondents that are either extremely unlikely or extremely likely to purchase are less affected. The first choice model reflects differential impact on the extreme, a stair-step probability function. Once a product alternative reaches a certain threshold of utility, it is chosen with certainty. Moderate changes in a product's utility have no impact on respondents with relatively low or high probabilities of purchase. A gain in shares of preference reflects gains of respondents on the cusp. With differential substitution, we find that a new product offering should take share disproportionately from similar ones. Simulators that reflect differential substitution are necessary to accurately model actions like product line extensions or Me Too product imitations. The first choice model reflects differential substitution at the extreme. Identical products split share that would be captured by just one of them. They split it exactly in half with near identical products, so the winner takes all. However, the real world reflects some degree of random buyer behavior, and near substitutes should reflect some degree of share inflation beyond that suggested by the first choice model. Differential enhancement. Pairs of highly similar product alternatives should display extreme probabilities of choice. The slightly better product should strongly dominate the other. We are assuming that everything about these two trips to Paris are identical, except for the price. The first choice model reflects differential enhancement at the extreme. The slightly dominant alternative of the pair is always chosen. In our illustration, the trip to Paris costing $3,000 is always preferred to the trip to Paris costing $3,001. The real world reflects some degree of random buyer behavior, so we shouldn't expect the slightly dominated alternative to have a zero probability of choice. So, how realistic is first choice? The first choice model is simple to do and easy to understand. Unfortunately, it is a patently false model of consumer behavior. It is an extreme model that assumes a product barely preferred over another is chosen 100% of the time. It is also a less efficient use of data. We learn about which product is preferred, but don't capture anything about relative preferences of not preferred options. Furthermore, standard errors of simulated shares are relatively higher than Logit. Despite the theoretical problems, there are certain conditions under which first choice can work quite well. We'll later show a more flexible, tunable approach. Buyers never purchase with 100% certainty the product our model says is most preferred within a set. Some random behavior occurs. Other influences, such as out of stock or children in the cereal aisle, can alter choice. And there's variety seeking. How do we model uncertain behavior? For each respondent, perhaps we can estimate continuous probabilities of purchase rather than 0% or 100% for each alternative. We often call this vote splitting. So with the first choice method, we would give one of the options 100% of the vote. But in the share of preference, we're going to split the votes among all three alternatives. But how do we do that? With the Bradley-Terry-Luce, or BTL, choice model, we assume three product alternatives with independent choice probabilities as follows. A equals 25%, B equals 20%, and C equals 5%. If these three are the only alternatives available, the probability of choosing A is equal to the probability of A divided by the sum of the probabilities of all three alternatives. In this case, 25% divided by 50%, which equals 50%. Note that the BTL model requires that independent probability of the product alternative be known. It is a mistake to use the BTL model with conjoint part worths whose scaling do not reflect probability estimates for the product alternative. For example, we know that a negative utility sum for an alternative cannot work. The BTL rule, as well as the more popular Logit rule that we'll introduce shortly, is not without its problems, however. One of the most potentially problematic properties is known as independence from irrelevant alternatives, or IIA. It basically says that the ratio of any two products' shares should be independent of all other products, and all other product alternatives are irrelevant to that relationship. An improved product gains share from all other products in proportion to their previous shares. This is also known as the red bus, blue bus phenomenon. The illustration of the red bus, blue bus was created by early academics working in transportation research during the 1970s who recognized this potential problematic property of the Logit rule. Let's say that you had to commute to work and you had to choose between a car and a red bus. Suppose you choose between these two options with equal probability, 0.5, so that the odds ratio equals 1. Now suppose a third mode, a blue bus, is added to the mixture. Now if we assume that you do not care about the color of the bus, you will be expected to choose between the bus and car with the same equal probability, which means that the probability of a car is still 0.5, while the probabilities of each of the bus types is 0.25. But IIA implies that this is not the case. Under the IIA rule, a new product introduced into the choice scenario takes share proportionately from existing products. Because the blue bus and the red bus have equal utility, the new probabilities for the car must be 0.33, the red bus 0.33, and the blue bus 0.33, which means that we don't take into account the fact that the red bus and blue bus are very similar and may be substituted for each other. Now let's take a look at another example. Imagine a market with just 3 ways to get to work, with 20% preferring the red bus, 30% preferring a bike, and 50% preferring to drive a car. Assume a new alternative appears, a blue bus, with an independent choice probability equal to a red bus, also 20%. The red bus, bike, and car have to give up an equal proportion, or 16.67%, of their original share to make room for the blue bus. Therefore, the new shares would be blue bus at 16.67%, red bus at 16.67%, bike at 25%, and car at 41.67%. So is IIA realistic? Well, it is not realistic to assume that the blue bus takes its share proportionally from all of the alternatives. We should expect it to take a disproportionately share from the red bus than from the bike and car. The resulting net share for both buses is 33.33%, rather than 20% when only the red bus was offered. We call this share inflation for similar products. The Logit simulation model is much more commonly used than the BTL model, known as share of preference in Sawtooth software. It permits estimating continuous probabilities of choice for alternatives for each individual using vote splitting. It is more flexible than the BTL model because product utilities aren't required to be positive probabilities. It doesn't require part-worth utilities computed under Logit. For example, least squares regression, monotone regression, or linear programming may be used for Logit analysis. Now consider 3 alternatives, A, B, and C, in a choice set. The probability of choosing alternative A with a utility of U sub A in this set is described by this equation. In this case, P sub A is the probability of choosing alternative A. EXP means exponentiate or analog, or raising e to the power of the total utility, and U sub A is the total utility for alternative A, etc. In Excel, the exp function returns e raised to the power of a number. The constant e equals 2.71828182845904, which is the base of the natural logarithm. It's also known as Euler's constant. Let's work through an example. Let's assume 3 product alternatives with the following utilities, after adding up their respective part worths. Product A is 0.75, product B is 0, and product C is minus 1.25. Once we place the values into the Logit equation, we see that the share of A is 62%. And if we solve for B and C, we find that B is 29% and C is 9%. Here are some important properties of the Logit simulation model. IIA. Product utilities, U sub i's, can be negative or positive values. You can add any constant to all product utilities, and the shares are unchanged. And you can multiply the utilities by a constant, and the relative shares can be tuned flatter or steeper. We can also fine-tune our Logit simulations. And the way we do that is by multiplying all part-worth utilities by some particular value. Values greater than unity, or 1, cause relative shares to become steeper. Recall our earlier example where A had utilities of 0.75, B was 0, and C was minus 1.25. If we multiply those utilities by 0.01, 1, and 5.0, and then plug those values into our Logit equation, we get this table. At Sawtooth Software, we refer to the multiplier that is applied to all utilities as the exponent. With a very large scale factor applied within Logit simulations, it is essentially equivalent to first choice, where the best alternative gets 100% of the share. As the scale factor nears 0, it distributes the shares more equally across alternatives. Recall in our discussion that respondents don't always choose the product alternative with the greatest utility. The exponent scale factor within Logit simulations allows us to adjust the degree of uncertainty we could place on predicted probabilities of choice. Analysts apply exponent after utilities have been estimated. However, most utility estimation techniques already have scale factor reflected in their part-worth utilities. Consider the following CBC utilities for 2 respondents. Respondent number 1 with 1.535, 0.37, 2.612, minus 0.223, and minus 2.050. And respondent number 2 with values of 0.102, minus 0.097, 0.117, minus 0.055, and minus 0.132. Respondent number 1's utilities reflect a much wider range, a larger scale factor. His simulated shares will tend more towards 0 or 100%. Respondent number 2 was less consistent, displayed less sensitivity to differences in products than number 1 during the CBC survey. His simulated shares would be relatively flat. The scale factor evident from utility estimation reflects the degree of uncertainty suggested by conjoint judgments within the questionnaire. You may want to adjust the scale factor by a uniform additional degree to better fit actual market shares. Sawtooth Software's exponent does that. Or simply multiply all part worths by the desired scale factor using a spreadsheet simulator. Heterogeneity refers to the fact that people have different preferences. Market simulation models that reflect heterogeneity are usually more accurate and flexible than those that do not. When discussing heterogeneity, it doesn't just exist in one state. It exists on a continuum. For aggregate models, it exists as a single set of part-worth utilities that reflect the average preferences of a population. For disaggregate models, there are actually 2 subtypes: segment-based models, and individual-based models. For segment-based models, a set of part-worth utilities are developed that reflect the average preferences of each segment. For individual-based models, a set of part-worth utilities is developed for each respondent. The following chart illustrates the relative heterogeneity for a typical study. CBC Logit would be an example of an aggregate model with low heterogeneity. CBC Latent Class, a segment-based model, has more heterogeneity. And CBC Hierarchical Bayes, an individual-level model, has high heterogeneity. Why is capturing heterogeneity good? Because it helps reduce IIA, or the red bus, blue bus problems, which means it displays more accurate differential substitution and cross-elasticities. It can reflect, to a degree, higher-order interaction effects, even though explicit terms have not been estimated. It also better reflects an appropriate scale factor for different respondents or subgroups of the population. And it more accurately reflects differential impact, substitution, and enhancement in simulations. IIA troubles in simulations are significantly reduced by models that capture heterogeneity. With aggregate logit, the IIA problems are at their worst. With latent class, the IIA problems are still significant. And with individual level analysis, the IIA problems are significantly reduced. IIA still holds within the element or segment or individual of analysis. But when the choices are aggregated across elements, the resulting shares do not strictly adhere to IIA. Now, let's compare first choice versus logit simulations. Both methods reflect differential impact, but logit's uptake is smoother and usually more realistic. It is S-shaped rather than stair-step shaped. First choice often better reflects differential substitution, because logit suffers from IIA, though sensitivity of the substitution effect may be too extreme. As for differential enhancement, logit often doesn't reflect enough dominance for the preferred product of a similar pair, and first choice reflects absolute, usually too strong, dominance. Logit doesn't do a good job at reflecting appropriate differential enhancement because of the near equal probability of choice between slightly dominated pairs. The first choice method is essentially immune to share inflation of similar products. However, the first choice method is often too extreme, not tunable, and doesn't use data as efficiently as the logit simulation method, with higher standard errors of share estimates. The logit simulation method is tunable and more effectively uses data, with lower standard errors of share estimates. However, logit falls prey to IIA problems. Isn't there a way to get the benefits of both methods? Well, yes, there is. Randomized first choice, RFC, is a relatively new technique that shares much in common with both first choice and logit share preference simulation techniques. It can be used with aggregate or disaggregate utilities. It splits shares within the element of analysis, but reflects more accurate substitution effects for similar products than share of preference. It is also tunable, both in terms of scale and in terms of appropriate degree of share inflation for similar products. Before we continue, we should review the basic random effects model. The random effects model, created by Daniel McFadden in 1973, takes the form of U sub I equals X sub I times beta plus E sub I. In this equation, U sub I is the utility of the alternative I. X sub I is the row vector of independent variables, or the attribute level codes, that are associated with alternative I, which we get from our dummy-coded design matrix. Beta is the vector of part worths, and E sub I is a random error term. In other words, the utility of alternative I is a function of the utility of that alternative plus some random error for that alternative. The respondent chooses the alternative with the highest utility. Assume the utilities for Honda are 0.70 and Ford are 0.65 for one respondent or element of analysis. If the error is 0, then the utility of the Honda is equal to 0.70 plus the error of 0, which brings its revised utility to 0.70. And the utility of Ford becomes 0.65. So the respondent will choose the product with the highest utility, which is the Honda. But isn't that just the first choice model? Well, yes, it is. The respondent will choose Honda every time. But what if the error is not 0? Well, let's assume the error is a random value from 0 to 1 and repeat the simulated choice process 10 times for that one respondent, adding new error each time. Here are the simulated choices for 10 replications. As a result, Honda was chosen 6 out of 10 times, or 60% of the time, while Ford was selected 40% of the time. If the error is distributed as Gumbel, then the share predictions, after many draws, are nearly identical to Logit. It is calculated with this formula, where X is rectangularly distributed. Here are just a few numbers from a Gumbel distribution. Over many thousands of draws, the mean is around 0.58, and the standard deviation is around 1.28. The Gumbel distribution is a right-skewed, or not normal, distribution. The variance of E sub I tunes scale of shares in the same way that exponents tune shares in Logit. Adding larger error variance to the utility of each alternative is equivalent to applying a smaller scale factor, and share predictions are flattened. Adding less error makes the share predictions steeper. Adding 0 error to the utility of each alternative is equivalent to the first choice model. While REM is really cool, unfortunately, it doesn't do anything to solve the IIA or red bus, blue bus problem. It still exists because the error we added to the product utilities is independent. And adding a duplicate product in a simulation increases the net share to the twin products. But if we could somehow make similar products have correlated error terms, we could correct for product similarity. Consider the following products, A, B, C, and D. Each one is composed of 4 attributes and the following levels. As you examine this table, can you identify the product that is the most similar to the others? Or the product that is the most unique? Well, here's the answer. Product D has unique levels on all of its attributes. It is least similar to the others. Product A shares 3 attribute levels in common with other products, namely attributes 2, 3, and 4. Product A is most similar to others within this set. So, here's the translation. The utility of alternative I is a function of the utility of that alternative after adding some random error to the part worths, plus some error added to the product alternative. Note that E sub A is held constant for all alternatives, but E sub P is unique for each alternative. The E sub A term introduces correction for product similarity. Consider 2 products identical on 4 out of 5 levels. 4 out of 5 of error contributed by E sub A is identical between products for each replication. These products will compete more closely. They're highly substitutable. If E sub A is 0, then RFC equals the Logit model. If E sub P is 0, then duplicate products always get their share divided in 2, like a tunable first choice model in that case. So here's a quick summary of randomized first choice. First, RFC lets you tune the amount of correction for product similarity between an IIA model and one that splits share in half for duplicate offerings. Second, it is tunable in scale. And third, it reflects relative accurate differential impact, differential substitutability, and differential enhancement effects. Here are some of the weaknesses of RFC. It is not as easily understood or described as first choice. The most correct use of RFC requires carefully defined holdout concepts that reflect differential similarities among the product concepts within the sets. The default is to apply attribute type error only, or split shares exactly in half for duplicated offerings. The best use of RFC results from properly tuned attribute and product type error, which is time-consuming to do. So, which simulation method should you use? If the first choice technique best fits holdouts or market shares, then use that. Of course, that is rarely the case. Then if all products are equally similar or dissimilar, then use Logit or share preference. Note that with a two-product market simulation, the products are always equally similar or dissimilar to one another. And if there are more than 3 products in a simulation, and different degrees of similarity among them, then you should probably use RFC, especially if aggregating utilities through Logit or latent class. So, here are some big questions you need to ask yourself. How can I tell which estimation technique, Logit or latent class or HB, is best for my data? And how can I tell which model specification, i.e. main effects only versus interactions versus linear terms for quantitative attributes, which model specification is best for my data? And how can I tell which market simulation method is best for my data? Well, the answer is holdout choice tasks. So, what are holdouts? They are CBC-looking choice tasks that you put in your questionnaire but don't use to estimate utilities. We suggest that you include 8 or more, which you can block across respondents so that each respondent doesn't need to complete all 8. You then observe the percentage of respondents that choose each product concept, and you use the same product specifications as holdouts in the market simulator and predict shares of choice. Then, you compared observed versus predicted share of choice. Here are the assumptions that we make when using market simulators for conjoint analysis. First, that we have interviewed the right people. Second, that each person is in the market to buy. Third, that we have used a proper measurement technique. Fourth, that respondents have answered reliably and truthfully. And fifth, that attributes which affect buyer choices in the real world have been accounted for. And here are some more assumptions. Sixth, we assume that there is equal availability or distribution of the options. Seventh, we assume that respondents are aware of all products. Eighth, we assume that each option has a long-range equilibrium or an equal time on the market. Ninth, there is an equal effectiveness of sales force. And 10th, there are no out-of-stock conditions. Now, please keep in mind that shares of preference don't always match actual market shares. In fact, conjoint simulator assumptions usually don't hold true in the real world. But this doesn't mean that conjoint simulators are not valuable. Simulators turn esoteric utilities into concrete shares. Conjoint simulators predict respondents' interest in products and services, assuming a level playing field. Here are some final conjoint simulator suggestions. Number 1, simulators based on individual level conjoint data, a separate prediction for each respondent, are usually more accurate and flexible than simulators based on average or aggregate data. Number 2, beware of red bus, blue bus problems, which we call the share inflation for similar products. And number 3, Avoid the temptation to make shares of preference look like market shares using external fudge factors. And number 4, don't forget the assumptions. This concludes the presentation. Thank you for watching. For more information, please visit sawtoothsoftware.com.